Let's see the second method of representation of signed integers, that is 2's complement representation. So 2's complement is a clever way of storing integers so that the common math problems like addition, subtraction, multiplication and division is made very simple. So implementation of addition and subtraction becomes very easy when the numbers are represented using 2's complement method. So it basically says for zeros, you just use all zeros. So when you just compare this representation method with that of the sign to magnitude method that we have seen in the previous video, there we've seen that we have two representations for 0. So we have one for minus 0 and the other one for plus 0. So that is a bit confusing, and we cannot have two zeros, a negative and a positive 0. 0 can only be one, always positive. So always 0 can only be positive. That is the reason why we basically go for representing numbers in 2's complement method. And let's see how the 2's complement representation is done with signed numbers. Yeah, it's very simple. Like, we take all the positive numbers as such, and the negative numbers are represented using 2's complement method. Say for example, let's take the same mini bit of 4 bit values in binary. So it is 2's complement. 2's complement representation of numbers. And let's see how this 4-bit values can be represented using 2's complement. So 4-bit values, like for zeros, you just have zeros, all zeros. For 1, it is going to be 1. So this is 0 or plus 0. And this 2's complement representation naturally uses the MSB to represent the sign of the number. So whereas in the previous case, in the signed bit, that is in the signed magnitude representation, we had explicitly taken the MSB as the sign bit. So here, if you just look into the 2's complement representation, this last bit will automatically get converted into or changed into minus when we start writing the negative values. So let's see how it is happening. Here it is plus 1. Let's write all the numbers that are possible with 4-bit values. So here it is 1 0 0 0 1 1, and it is plus 2 and plus 3. How do I write this? It is 1 2 4 8, the place values, and now I just sum up the place values wherein I have 1 in the binary bit pattern and get the decimal equivalent of the given binary bit pattern. So here it is 8, under 8 we have 0, and here again in place of 4 we have 0. So it is 2 plus 1, so it is 3. And now the next possible combination is 1 in the last but one bit to MSB, and the other two are 0 0 0 1 and 1 0, and the other combination possible is 1 1 1. This is plus 4 plus 5 plus 6 and plus 7. Now we said that we are going to represent the negative numbers in the 2's complement method. So here if I take minus 2, then what I do is to represent this 2 as a negative value, I take the binary equivalent of 2, which is 0 0 1 0, and find the complement of it. That is, I just find the 1's complement of this number, that is 1's complement of 2, and add 1 to it, which is going to give us the binary equivalent of 2, minus 2. So this is minus 2. Okay, So now let's see how this sums up to be minus 2 when we use the place values. So here, as we said that this MSB is going to be used for representing the sign, I just take minus 8 here and all other bit positions are positive. Okay, now sum up the values wherein you have 1 in the near the place values. So this 1 is attached with 0, so here we are not going to consider this 1, and it is 2 plus 4 minus 8. So minus 8 plus 4 plus 2 sums up to be minus 2. That is minus 8 plus 6, which is equal to minus 2. So this is the right representation of negative 2. Okay, now let's see the patterns here. So the other possibilities are written, and also let's see what these numbers are equivalent to in decimal. So it is 0 0 1 1 1 0 1 0 here, and 1 0 1 1, and marking this as 1 and taking the other two values as 0. So it is 1 0 1 0 1 1 0 1. It should be 0 1 and then 1 0 0 0 0 1. 1 2 3. Okay, so here 1 1 1 0 is 2, that is minus 2, and this is 1 0 0 0, so minus 8 plus 4 plus 2 plus 1. So what this is equivalent to? So you don't take this 4, 2 and 8, so only left out number is minus 8. So minus 8 is represented as 1 0 0, and this is minus 7 minus 6. You can work it out and check. It sums up to be the equivalent decimal number what I write by the side of this pattern. So here it is 5 4 3 and 1. So how this is 1? It is minus 8 4 plus 2 plus 1. So minus 8 plus 4 plus 2 plus 1 is equal to minus 8 plus 7, which is equivalent to 1. So this last bit at every position here dictates the sign of the number. So it is minus 1 here, minus 5 here, and you could see that the number, the magnitude that is represented here after this minus 1 do not directly relate to the decimal equivalent of 5 as in the case of signed magnitude values. Whereas the signed magnitude representation for minus 5, what we actually write is, for minus we just take this 1 in sign bit position, and for 5 we just take the binary equivalent of 5, the decimal number 5. So it is not the complemented form of the number, it is direct binary equivalent of the decimal number. So here that's the difference between 2's complement representation and the signed magnitude representation. Signed magnitude representation has its own problems, where we have seen that it is going to have two zeros, one a positive 0 and the other one is negative 0. Right? So working with two zeros is not possible. We can have only one positive 0. There is nothing called as negative 0. And also addition and subtraction is going to be a bit difficult compared with 2's complement arithmetic operation. So normally the computing systems are going to apply this 2's complement representation technique in order to represent signed values, which actually eases the building of components for subtraction, division, multiplication and addition. Let's now see how can we do addition, subtraction and other arithmetic operations using 2's complement method. So basically we work with addition and subtraction, and multiplication and division are implemented using addition and subtraction. So let's see how addition and subtraction could be done with 2's complement representation. So here again the numbers that we work with can occur in different forms when we try to apply addition and subtraction. That is, if I do addition, the various possible combinations of numbers which could be added or say both positive and one number being positive and the other number being negative. So the other possibility is the first number being negative and second being positive, and the other combination that is possible is adding two negative numbers. So in the case of signed magnitude representation, we have to check whether the signs are same or different, and if the signs are different then we have to apply subtraction, and there again we have to find out whose magnitude is greater, and then do the complementation and then subtract and get the result. So the process is tedious in the case of signed magnitude representation, whereas that is going to be very very easy in the case of the 2's complement representation method. And let's see how it is easy by taking some examples. Let me take say the numbers 3 and 5, and before that let us also understand the range of numbers that could be used when we use n bits to represent number in 2's complement form. So if you have n bits to represent, then the range of numbers that we can work with, or allowed range of numbers with n bits, are minus 2 to the power n minus 1 to 2 to the power n minus 1 minus 1. So you can just verify it with 4 bits that we have tried in the previous slide, that is minus 2 to the power 3 to 2 to the power 3 minus 1, which means that minus 8 to 7. So this is what is possible. You could see here. So when you have 4 bits, then the minimum number is 0. Minimum number is minus 8 and the maximum number is plus 7. Right? And you could also see that we have only one representation of representation for 0, and it is not 2 as in the case of the signed representation, signed magnitude representation. Hope this is clear. And now let's try to add some numbers. Let's take 5 and minus 3 minus 8 added with 7 let's take minus 5 and minus 7, and also let's take minus 2 plus a minus 3. So here are cases where we get values out of range. Since we are working with 4 bits, the minus 5 and minus 7 sums up to minus 12, whereas this minus 12 is not within the range of the numbers when 4-bit representation is used. Whereas here this is right, and you're going to get minus 1 in this case, and the result of this will be 2, the result of this will be 8, and again this is overflow, that is we don't get the value within the range, it is going out of the range. So here it is overflow, it just crosses the max. So if it crosses the max, then it is overflow. If it crosses the min, then it is underflow. Right, let's see how this overflow, underflow and the right results could be easily recognized by system when we do operation with arithmetic operation with 2's complement method. Now let's take the first example. So example 1, add 3 and 5. So what is the binary equivalent of 3? It is 0, 0, 1, 1. And binary equivalent of 5 is 0, 1, 0, 1. Okay. Now you just try to add. It is 0 here, carry 1, and 0 again, carry 1, 0 and carry 1. And summing up this value you get 1, and you don't get any overflow or any end around carry. We call this as end around carry. And this is the carry in of the sign bit. So here when we work with 4 bits, we know very clearly that the last bit is a sign bit. And to understand whether the result what we got is a right result or not, we're going to check these two values, the carry values. That is carry into the sign bit position and carry out of the sign bit position. So this one is carry in to the sign bit. Okay, and this 0 is carry out of sign bit. So we're going to consider these two values, and if these two values are different, then we can determine that. So if you just look into this number is equivalent to minus 8. Should the answer be minus 8 or plus 8 here? It should be plus 8, because both the numbers that are getting added here are positive and there is no chance of getting a negative result. So, but here in this case we get a negative result, because why I say that this is negative is the sign bit has got value 1 in it. And you could also see that this bit pattern 1 followed by 3 zeros represent minus 8 in 2's complement method. So this is wrong, this answer is wrong. And this wrong answer could be identified using the bit values in carry in and carry out of these last two positions. So if the bit values are different, if they are 0, 1 or 1, 0, then the result is either a overflow or underflow result. We could check that. For other cases that will be same. These two bit values will either be 1 or it will be 0. And let's check that. So okay, anyway, this is wrong and this is overflow. So that overflow is determined using the sign, that is the carry into the sign bit and carry out of the sign bit. Okay, now let's proceed with adding the next number. It is 5 and minus 3. So 5 and minus 3 is 0, 1, 0, 1. And what is minus 3? You're going to have 1 here, and it is minus 8, then you have to subtract 5. So you're going to have 1 in these places and 0. So this is minus 3. Okay, in 2's complement form, we can check that. Minus 3 is 1, 1, 0, 1. That is what I've written here. How I directly wrote is, I've just taken this value minus 8 and I want to arrive at this number minus 3. So to convert this into minus 3, I have to add 4 and 1. So add 5 to minus 8, you get minus 3. So I've just put 1 in these positions and the remaining positions were filled with zeros. That is how this number was arrived at. So now adding these two numbers. So when you add, what happens here? It is 0. A normal binary addition is being carried out here. It is 1. 1 plus 1 is 0, carry 1. 1 plus 1 is 0, carry 1. And this is end around carry. So this is a overflow bit or this end around carry, and it needs to be discarded. So we are not going to consider. Anyway, this is not going to be there in the accumulator after applying this operation, because accumulator's size is only 4 bit. So it can only store these 4 bits, and this 1 will get vanished. It will just be dropped. Now, to check whether the answer what we got is right, I said that we have to check for the sign, the carry into the sign bit position and the carry out of the sign bit position. So carry into the sign bit position is 1 and carry out of the sign bit position is also 1, which means that they are same. So if they are same, then whatever result you have in the accumulator is the right result. Now we can check. The result that we need to get here is 2, and the binary equivalent of, decimal equivalent of this binary bit pattern, leaving this 1, because this end around carry, it is not going to be there in the accumulator, so we will not have this 1 at all, right? So leaving this 1, compare the or check the decimal equivalent of this 0 0 1 0. So decimal equivalent of this number is 2, and the sign bit is 0, so positive. So the answer what we got is right here. Moving on to the next example, it is -8 and +7. So what is -8? It is 1 followed by 0. So I am just writing all the numbers in 2's complement form, because we are working with 2's complement arithmetic. So it is, what is 7? 7 is going to have 0. This is positive, so 0 in sign bit position, and we have 1's here. So now add these two values, what you get, it is 1 1 1 1. Did you get any carry here into the sign bit position? No, it was 0. And we also did not get any carry here after adding the sign bits. So the sign carry out of sign bit is also 0. So we have 0 0. The values are similar. If the values are similar, then the value what is there in the resultant position or the accumulator is right. So here the number is 1 1 1 1, which means that something negative. And what is the equivalent of this 4 ones? It is -8. I'm sorry, it is -1. It is -1, because here it is -8 and you have all these bits to be 1. So 4, 2, 1 summed up together will get you 7. -8 plus 7 will be -1. So this is -1, wherein that is the result expected by the user after applying plus on these two numbers. So this is right. We could see the thing that is important to verify here in order to check whether we have the right result after carrying out this operation is checking the carry in and carry out in the sign bit position. So when those two are same, the result whatever we have in the accumulator is the right result. Now we can try with -5 and -7. So -5, let me take the fourth example, -5 and -7. So binary 2's complement of -5 is 1 here, and 5, you need to have 5, so you have to subtract 3, 1 1, and for 7 it is 1 and 1 here. Now add these two numbers. 1 plus 1 is 0, and 1 plus 1 is 0, carry 1, and here it is 0, carry 1, 1, and here it is, there is no carry here. 1 plus 1 is 0, carry 1. Now check the carries here, the last two carry bit values, and then try to access the value in the accumulator for further processing. So if these two are similar, then whatever you have here is right. If these two are not similar, then the result is wrong. So here this works out to be plus 4, where adding minus 5 and minus 7 should get us to minus 12, which is out of range. You get a wrong result. So that could be realized using this bit values in the carry. So addition is as simple as that. Just take the numbers in their natural complemented form, 2's complemented form, and simply add. If there is an end around carry, discard it and take the result. If there is no end around carry, or in any case, you have to check for the bit values in the carry. So the end last carry, that is a carry that is coming out of the last bit, and carry that is fed into the last bit of this organ and add in, has to be checked. So if both are similar, then the result what you have here in the accumulator is right, or else it should either be an underflow or overflow. So that is all about addition. Now let's see how subtraction could be done with 2's complement method. So the subtraction actually is very direct and simple. All that you need to do is take the 2's complement of the subtrahend. So you're going to have minuend and subtrahend, that is you're going to have, say, A and B. So if you want to subtract B from A, then negate it and add. If you want to subtract B from A, so instead of doing A minus B, what we do is we just take the negative value of B and add it. Let me show you with an example so that it will be more clear. Subtraction of 2's complement numbers. The possibilities or the various combinations that are possible are A minus B, minus A, minus plus B, A minus minus B, or minus A minus minus B. So in all the cases, this subtrahend is going to be complemented and then added. This could be written as A plus minus B, and this could be written as minus A plus minus B. This could be written as A plus minus of minus B. Okay, and this could be written as minus A plus minus of minus B, which is nothing but A plus B and minus A plus B. You'll get the results right. Let's try some examples, numerical examples, so that it will be clear for you. Let me take few examples. For example, let's take minus 5 subtracted, so plus 3 subtracted from minus 5. So how do you represent minus 5 in 2's complement? It is 1, 1, it should be 5. So here minus 8, 4, 2, 1. You have to subtract 3 from this. So you have minus 3. So this is minus 5. So what the rule says, so if you want to subtract, then negate the subtrahend and add it. So what we are going to do here in this case is we take minus 5, add minus 3. Instead of taking plus 3, complement the subtrahend. So find the 2's complement of 3. So here it is 3, so minus 3 is nothing but 2's complement of 3. 2's complement of 3 will be 1. So you're going to add minus 3. Okay, so it is 1 and 1 here, 0, 1. Now you add these two numbers. That is 1 plus 1, 0, and carry 1 here. So 1 plus 1, 0, carry 1, 0, carry 1, so it will be 1 and 1. So you have 1, 0, 0, 0, which is nothing but minus 8. So the answer is right because apply the same rule here. There is no change in rule. So only thing you have to keep in mind for subtracting numbers is take the complement of the subtrahend and then add it with the minimum. So basically you're going to do addition by complementing the second number and adding it with the first number. So that gets you subtraction done. You could see here it is minus 5 minus plus 3, which means that minus 5 minus 3 equal to minus 8. That is what we have got here. The result is right because this is within, we have the right result. Let's try with some other example. Maybe I'll take another number, minus 2 minus 8. So what we are trying to do here is subtract 8 from minus 2. It is a plus of minus 8. So what is 2? It is so here 2 was 1, 1, 0 plus minus 8 is 1, 0, 0, 0. Now add, what you get is, here it is 0, 0 and 1. 1 plus 1 is 0, carry 1. So if you just look at these two values, these two are different. So if the values here are different, here the answer what you have is wrong. You could see or sense that it is underflow, because you need to get minus 10. So minus 10 is not within the range, it is lesser than the minimum value that could be represented using 4 bits. So it is underflow. Whatever answer you got here is wrong, so that has to be intimated. And let's try with one more example. Mm, 3 minus 5. So 3 is, so we'll just complement minus 5 or negate minus 5 and add with 3. That's the idea. That's the idea. Here 3 is 0, 0, 1, 1 and minus 5. So negate minus 5. So what is minus 5? When you try to negate minus 5, it becomes plus 5, isn't it? So minus of minus 5 will become plus 5. So here you add 5. It is 0, 1, 0, 1. So here it is 0, carry 1, 0, carry 1, 0, carry 1, 1. Zero. You have 1 0. So 3 plus 5 is what? 3 plus 5. Add this and take this minus inside. That is what we do here. This is the case that is to be considered. So you need to do addition of 3 and 5. So addition of 3 and 5 is 8. But here it is showing us minus 8. So this bit pattern is equivalent to minus 8 in 2's complement. Alright. So the answer what you get is wrong, and that could be sensed using this bit values. So 0 and 1. The values are not similar. The carry values are not similar. So it is out of range. So implementing 2's complementation is 2's complementation arithmetic is very easy. In both the cases, both in addition and subtraction, you're going to basically do addition. So just one unit of adder is needed in order to implement both addition and subtraction, whereas in the case of find magnitude representation, you need to have a separate system wherein we need to check the sign of the values, and the magnitude has to be accordingly adjusted and subtracted in the case of subtraction. So all this cumbersome work that the sign magnitude representation requires is being overcome with this 2's complement representation method. So the hardware unit for 2's complementation arithmetic is very simple, and when compared with signed magnitude representation method. So that is all about addition and subtraction of 2's complement numbers. Multiplication of binary numbers in the next video.